Hello, good day, and welcome to another lecture on advanced plasticity of solid continua. So today we will be discussing about thermodynamic closure and the Coleman-Noll procedure. Now before we start, just a word about what we mean by thermodynamic closure. So we are talking of doing the constitutive relations, that is relating the forces to the fluxes or the constraints to the reactions or the other way around, so that your system of equations are complete. That means they can be actually solved. For example, in elasticity, if you do not relate the stress to strain, then you cannot really determine deformation, right? Deflection, if you want to determine, you need to relate the stress to strain. So this is what we call as thermodynamic closure, and we see that this is an important thing, and there has to be a guiding principle which is provided by the Coleman-Noll procedure and doesn't change from problem to problem, by which we actually account for the two laws of thermodynamics. So this is what the subject of this today's talk is. So let us get going with that. Let us take a look at the constitutive laws and thermodynamics first. So as I was saying, which constitutive laws are compatible with the laws of thermodynamics? That is the question. So Coleman-Noll principle offers a guide, but it is a very general guide which doesn't change from problem to problem, as I have already said. So that is why it is very useful. But that doesn't mean that the Coleman-Noll principle actually solves for you the constitutive laws. That means it doesn't directly give you the constitutive laws. You have to still apply your mind from problem to problem, but it gives a guiding principle. The important idea here in applying the Coleman-Noll is the independent specification of rates. So when we talk of rates, we talk of rates of certain quantities, no? So when I say independent specification of rates, it means the independent specification of those quantities and their rates. When I say independent specification, it also means that this specification is local. That means we are only working within a small neighborhood of a point. Again, the tangent space structure comes in, because tangent space captures that information of local neighborhood of a point, right? So it is only locally that we can actually have an independent specification of rates. That has to be remembered. It's a very important point. But before going into plasticity, just to make you quite acquainted with the basics of this Coleman-Noll principle, we'll use elasticity, thermoelasticity, or rather we will start with thermoelasticity and do elasticity as a special case, a rigid body heat conductor, and then we will go for plasticity. Okay, so then by the time we go to plasticity, we will be comfortable with the application. Now to start with, let us recall the local balance equations. So recall that we have the balance of linear momentum, which is given by the inertial force is given by the divergence of the stress and the body force, correct? Then the balance of angular momentum, which just states that the stress has to be symmetric. All of these force balance is in terms of stress. We have not yet talked of deformation directly within these equations, except that there is a deformation coming here, that is all. But stress has to be related to deformation also, right? So now the balance of energy also, which is the first law of thermodynamics, also plays a role, because when we actually do that connection between stress and strain or stress and strain rate, etc., then we have to satisfy the first two laws of thermodynamics. The first law is simply that it is in the form of a statement of balance of power. That means where E is the specific internal energy, then this is the local form of the balance of power. So it simply says that rho E dot is equal to there are three parts to it. One is the stress power, sigma inner product d. D is the rate of deformation tensor. Please recall the previous lectures regarding the definition of D. Then there is a divergence of the heat flux Q, right. Q is a vector, please recall, and there is this additional term which is the internal or the heat source per unit mass. Okay. So typically in most of our applications we will take the heat source to be negligibly small or not there. Okay. So now recall that R, the heat source, is a scalar valued quantity, Q is a vector, and so on. E, this specific internal energy, is also a scalar. Right, so we are ready to go further. Also recall the second law, which is that also it is called the Clausius-Duhem inequality in its local form. If S denotes the entropy or the specific entropy, then rho S dot must be greater than or equal to the minus of divergence of Q by theta, and the added to it must be the term rho R by theta. Okay, theta is the absolute temperature, it has to be greater than 0. Okay, so now we can actually combine the two laws. That means just let us remove R, actually eliminate R from these two equations. Then you immediately get this form. This combines the two laws, as you know from our previous discussions. It is called the dissipation inequality. It simply says that rho times E dot minus theta S dot etc. equal to this right hand side quantity. Okay. Now the thing is that also at this stage recall that this how this free energy comes up. It comes up through this term, because the internal energy contains all sorts of energetic terms, I mean including the terms that comes as part of the elasticity, which is entirely reversible, and the terms due to the heat flux etc., and the terms which are irreversible, entirely irreversible, like the plastic plastic strain rate etc., the terms involving those. So it is not really a very good way of separating the reversible irreversible things. So that is why we use another form of it based on the notion of free energy. The free energy changes this structure, makes this reversible irreversible connection quite explicit, and it follows the notion of internal free energy follows from this form of this equation. So we define the Helmholtz free energy, which is psi equals E minus theta times S. Okay, and then we rewrite in terms of psi, not in terms of E, the dissipation inequality this way. Okay. Now so this inequality basically is the starting point for applying the Coleman-Noll procedure. Okay. So let us describe first this procedure in the context of thermoelasticity. Okay. And then the elastic case will follow as a special case, right. So this is a very important part of our whole thing. So please keep in your mind the dissipation inequality all the time. Okay, so here we go with thermoelasticity. First of all, in doing this you have to have a functional assumption of psi. You have to understand what psi can depend on based on your understanding of the underlying physics. So in this particular case, that is in the case of thermoelasticity, let us say that psi definitely has to depend on some strain like quantity. Instead of strain, I can make it to depend on the deformation gradient based on which I can construct my strains. Okay. So that is for sure. But we are talking also of thermoelasticity. So I expect, or you would expect, psi to also depend on the temperature theta. Agreed? So we take psi as a function of F and theta. Then apply chain rule on this psi. This is a standard procedure. So therefore psi dot dot means differentiation with respect to time, which is equal to del psi by del f inner product with f dot plus del psi by del theta theta dot. Remember that del psi by del, even if you take the partial derivative of a scalar valued quantity like psi with respect to a tensor like f, then it becomes a tensor itself. So, that is why this Frobenius inner product comes in, this colon, right. And also recall that theta is a scalar. So, del psi by del theta is also a scalar. So, this del psi by del theta times theta dot is a simple multiplication of scalars. So, now you can use this expression for theta dot in the dissipation inequality which we had on in the previous slide. Okay. So, because there was a term psi dot there, right, recall. So, just put this psi dot, the expression for psi dot there, and rewrite the dissipation inequality in this form. Okay. So far so good, no issues. Now what we can do is as follows. Okay. So, first note that d is related to the deformation gradient and its derivative, time derivative through this identity. Okay. So, basically d is nothing but f dot, except that d is a purely spatial tensor, f is a two-leg tensor, so is f dot. So, therefore, you need all these f inverse and all that to make it live in the same configuration, all right. That is fine. Now, the symmetry of sigma, okay, also you have to use there on this, okay, actually to come to this following, yeah. So, there is some mistake here, I think this is sigma, yeah, okay. So, basically something was missing here. So, essentially what it means is that we can manipulate algebraically this a little bit to write this stress power in this form, all right. Then we can use this particular identity given here to rewrite the dissipation inequality, because sigma d, the stress power, comes as part of the dissipation inequality. Okay. Rearrange a bit to write the dissipation inequality in this form. So far it is only pure algebra, so there is no difficulty in that. You have to probably sit with a pen and paper and make sure that these expressions really make sense by doing the algebraic manipulations. Here comes the important claim, which is the crux of the Coleman-Noll procedure. The claim is that whenever you see a quantity, in this particular case by quantity I mean this f and its time rate, in this case by the time rate of f I mean d. Recall again that d is not a direct time rate of f because of this nature of d is being spatial, but it is basically if you pre-multiply by appropriate things then you get back this. So, basically at heart physics wise d is the time rate of f. Here we have theta, here we have outside theta dot. Okay. So, whenever you have a quantity like f or theta and the time rates, the important claim here is that these can be specified completely independently. Specifically in this case we can say that fd, theta and theta dot are all independently specifiable in a local sense. Recall that in this case other than this theta, all these other quantities f, d and theta dot are derivative of something. F is the derivative of deformation, d has two layers of derivatives. It is the derivative with respect to x of deformation, it is also the derivative with respect to time of deformation, all right. Theta dot is the derivative with respect to time of theta. Okay. So, these are all derivatives in some way or the other, right. So, other than theta, f, d and theta dot are all tangent space quantities, all right. So, now let us understand what we really mean by this independent specification, all right. This is what is called the local kinematic richness. First, let me give you a direct example. A proof of this, a constructive proof of this is available in the online notes that we have put up alongside these lectures. But for the time being, let us see how it works, or what exactly is at the heart of this statement. So let us take a deformation phi, which is of course small x in the range. Let this deformation be such that at time t0, that is the initial time, let us say, or some fixed time t0, and at some point x0, capital X0 means in the material body or in the undeformed configuration, the deformation gradient corresponding to this is f0, all right, and the theta is specified as theta 0 at the same point x0 t0, all right, in space time. So theta 0 and f0 are specified. f0 follows directly from this deformation phi, okay. Now comes the important thing. So we can, given this, that given f0 and theta 0, we can prescribe any arbitrary d0 and theta 0 dot at that point x0 t0. This specification of d0 and theta 0 locally does not have to come from f0 and theta 0, you understand. So basically what it means is that there exist other smooth deformation fields and temperature fields such that your d0 can actually be correspondent to those deformation fields which need not be this phi, something else, okay. So d0 at d at x0 t0 will be d0, theta dot at x0 t0 will be theta 0 dot. They are locally independently specifiable, independent of f0 and theta 0, right. So in that means while I specify d0 and theta 0 dot, f0 and theta 0 remain unchanged. So for a constructive proof, as I said, you can actually go to the online notes, but let me give you a feel of this here, okay. What it means is that let us actually construct it. So choose a point x0 t0 in space time. So consider a constant tensor f0, okay, such that of course f0 has to be such that its determinant is greater than 0. Now therefore for the original motion phi, as we have already said, grad x phi with gradient with respect to capital X at x0 t0 will be f0, no doubt about that. Also choose now arbitrarily something, any symmetric and constant tensor d0, okay, anything that you know, but it has to be symmetric and constant. Now define a new motion. We already had that motion phi. Now define another motion phi tilde, okay, at x and t, not necessarily at x0 and t0, starting from x0 t0 of course, such that phi tilde xt is x0 small x0, that is phi 0 itself, plus exponential of d0 times t minus t0 times f0 times x minus x0. You must understand the overall thing here, the structure. So this is a vector. Vector means it consists of 3 components in that sense. It is not a vector in the sense of an infinitesimal object that needs to be integrated living on the tangent space, not that way, okay. So this is also a vector. This quantity is the exponentiation of a 3 by 3 matrix d0 times t minus t0, correct, and the exponential of a 3 by 3 matrix is also a 3 by 3 matrix, you should know that. That is multiplied, that 3 by 3 matrix is multiplied by f0, which is also a 3 by 3 matrix. The result is also a 3 by 3 matrix, that is multiplied by x minus x0, which is a vector, Okay. So, the result is a vector. So, you must see these connections such that the terms in the expression all become consistent. The important thing here is that now based on this prescription of phi tilde, if you now find your f, so what is the corresponding f0 for this phi tilde? What is the corresponding deformation gradient for phi tilde at x0 t0? You can easily differentiate, okay, and directly find that it is nothing but f0, because at t0 this t minus t0 is 0. So, the exponentiation of this whole quantity becomes exponentiation of 0, exponentiation of the 0 matrix, which is the identity matrix, right, x minus x0. So, basically so x minus x0 vanishes because you take the gradient with respect to x. So, this becomes, you know, identity again. So, basically f0 remains. So, you understand that this is true, correct, we just saw. But in doing so your d0 has been entirely arbitrary. I did not bother about any connection between d0 and f0, right. I chose d0 as any arbitrary symmetric matrix, constant matrix, right. So, that is the basic idea, that is locally, you know. So, think of a point, you know, in the material body. This is my point, you see the point. So, think of the tangent space here, think of a curve that actually goes through it. This is my original curve, but this tangent space actually is such. So, I should actually make it very clear, so that I can, you know, this curve actually need not be fully on this tangent plane, it is curved, no. So, basically it can be locally on the tangent space and go off, right. So, I can actually construct another curve on this, in which it will be something like this. So, finally you will see the local correspondence of these two curves on the tangent space, they are only locally the same. Far away they will be quite different, right. So, in other words, if you now take their derivatives, for example, let us take another picture, okay. So, this is my tangent space, this is my point, some curve is coming from below, let us say. So, I mean I will just draw it like this, it is crossing it here, remaining in the tangent space a little bit and then leaving it, okay, upwards, let us say, all right. Think of another curve which actually goes like this, it is coming from below again, it is coming to the tangent plane here, it is crossing here and going off. So, at this point locally if you look, they are very close, right, but actually they intersect each other. So, at that point they are exactly the same, but their rates are entirely different, is not it. So, basically this is the idea of locality which is exploited here to understand that the rates and the original quantities can be specified in an independent manner, only locally, right. So, now if it is true, then let us take a look at the dissipation inequality once more. So, this is my dissipation inequality rewritten for you. This is my original quantity, this is my rate, d I can choose locally again, because I am interested about a point here, okay. When I go off I will apply this again, when I go to some other point I will apply this again, okay. So, there independently specifiable means what? So, theta dot and theta are independently specifiable, correct. What does it mean? That means that this quantity which is the coefficient of that rate must vanish. Why? Suppose it does not vanish, okay, it is something else, it is non-zero, this circled thing. Then you can never all the time get greater than equal to 0 on the right hand side, because I can choose, suppose you have chosen some d for which it is indeed greater than equal to 0 and this circled thing is non-zero. Then I can, because I can choose d entirely arbitrarily, so therefore I can choose some other d to ensure that now if you evaluate it, it will be less than 0, correct. I can always choose that, maintaining the symmetry of D. Exactly the same thing is valid for theta and theta dot. If you understand this, then you have actually grasped this basic idea behind the Coleman-Noll procedure. So, the basic idea here again is that this circle thing has to be equal to 0, correct. So, therefore, we have got something very useful. We have actually got the stress strain relationship. I mean, not really stress strain, in this particular case stress versus deformation gradient relationship. But suppose I consider my psi, instead of being a function of the deformation gradient, as a function of the strain itself, which I can easily do, then I can write stress strain relationship also this way, okay. So, because of the same logic. Now, from here we get another very interesting thing. This simply says that the entropy must be equal to the negative of the time derivative of the free energy with respect to temperature, okay. So, then what actually happens if these are 0, these circled things on the top, if these are 0, then they do not produce any dissipation, right, because this is 0 times D, 0 times theta dot, correct. They do not produce dissipation. What leaves the dissipation still positive? This quantity, what is left, okay, for which we really cannot apply this. So, this is called the reduced dissipation inequality, whatever is left after applying the independent specifiability of rates in the Coleman-Noll, okay. So, this is the basic idea of applying the Coleman-Noll, the independent specification of rates vis-a-vis the original quantities locally. Think of the tangent plane all the time, okay, or tangent space all the time to understand this physically, okay. So, now we can actually therefore look at the much reduced version, the reduced dissipation inequality, which simply, as we saw in the last slide, is that the negative of the Q, which is the heat flux, dot producted with grad of theta must be greater than or equal to 0, because theta below is definitely greater than 0, or I can say Q dot grad theta must be less than or equal to 0. So, basically what it means is that the heat flux, if Q dot grad theta is less than 0, it means that the heat flux must be directed against the temperature gradient, correct. So, heat must flow from high temperature to low temperature instead of low to high, correct, because high temperature to low temperature is a negative temperature gradient, right. So, this is understood, we know that intuitively, heat always flows like that, but this is how it comes naturally, okay. So, one way of satisfying this is to use the Fourier's law, as you know. So, for example, in Fourier's law, Q, that is the heat flux, is written as a negative of the gradient times some constant k. This k can be taken as a scalar valued constant, it is called the conductivity. So, we may be happy with a scalar conductivity, or k can be a symmetric positive definite matrix also. In that case, we call it a conductivity tensor. We need not bother about this, consider k to be a scalar conductivity, but definitely greater than 0. Then substitute this Fourier's law in the reduced dissipation inequality and immediately see that this is almost a squared quantity, k times grad theta transpose grad theta. It is something like A transpose A dot A. So, you see the positivity how it is coming up. Okay, so, this is what basically is the basic Coleman-Noll procedure. Now, we will take a breather here, and then we will start applying the Coleman-Noll procedure to the different classes of problems that I have already mentioned, thermoelasticity to start with, after we come back. Thank you for your attention, and we will come back soon.